even before I get carried away with this week's episode?
I'm good, thanks, Tim. It's been a hectic first week of term, the usual sort of meeting all the new students, seeing their bright, fresh faces. So hectic, but good.
And our listeners won't know, but there's a shiny new building in Oxford where my office is. And you actually taught in there. You were one of the first people to go in and teach, weren't you?
Yeah, so taught in there on Tuesday. It is shiny. It's the lecture rooms are really nice and spacious. It was a really nice experience.
Excellent. And so you didn't send all of the undergraduates to sleep then?
I mean, I may well have done, but the space was lovely.
And were you lecturing on a quantum computer?
Aha. Sadly, no. Sadly, a boring classical machine. But no, these new quantum computers do sound intriguing.
There's been a lot of news about them in the press recently, and how they, could, be another thing that changes our world. But I don't think they necessarily work particularly well at the moment.
No, I think that's right. I think they're doing actually one of my former PhD students has gone to work in this area. So he's been telling me a little bit about it. I think at the moment my understanding is that the potential is huge, but what we have in reality is still very much at the beginning.
Okay, so I know very little about them, but our guest today, Professor Ian Walmsley, is an expert on them, and actually he's just heading up a sort of a centre in Oxford all about quantum computing, and so he understands how they work better than most, I think. So should we get him on?
Yeah, let's do that.
So, welcome, Ian. Thanks for joining us. Well, I wonder if you'd like to start just by giving us a little bit of a background of what your current job is, who you are, and how you got here, actually.
Sure, Tim Simon, thank you very much for the invitation to come and speak. Yeah, well, I am a physicist by background, and then sort of I think of myself partly as an engineer by avocation. But I started out as an undergraduate at Imperial, then went to grad school in the US, then returned to the UK to Oxford in 2001. Spent a few years here building up a research group in the quantum domain and latterly in quantum information and quantum computing. Then I went off to Imperial to do some different stuff for a while as provost there. I've just returned now as the director of the new Oxford Quantum Institute, which is a university-wide initiative to try and build on the very great strengths of the university across this domain. And I hope to set the agenda for the future.
Well, welcome back to Sanity after a spell at Imperial. So, Simon, do you want to kick off?
Yeah, so I mean, yeah, intriguingly there you sort of said quantum and computing, two words which until very recently, I guess, not have not always been, you know, juxtaposed. And I'm a computational scientist, so I do calculations. So I thought I understood computing, but now things have changed. So can you just explain to us, our listeners, what you mean by quantum computing?
Certainly, Simon. Let me maybe start with a bit of history though, because I think it's quite interesting to understand how this conception came about.
Mm.
Um, and it started really with a an increasing knowledge in the, well, from probably from the 40s, 50s, 60s, from the earliest days of building digital computers, that it was extremely difficult to build simulations of even very small systems, uh, large molecules, collections of atoms, etc. And the reason for that is just sort of the fundamental mathematical structure that you use to describe the quantum world, which meant that problems grow exponential in complexity. We could talk about what that means later, with the size of the system. And so I think Richard Feynman was the first to articulate the concept that if it's that hard to simulate a quantum system, maybe the quantum system itself had the capacity to do much more computation than we knew how to do with sort of von Neumann Turing style computers. And that was the sort of start of it. And then over the course, that was sort of early 80s. So over the course of the next 20 years, a number of the key issues were resolved about how to do that. Perhaps we can come back to what those are later. But that allowed this concept to start to become a reality. And if one tries to point to a sort of key difference, it's probably the following, that in a regular current gen computer, one uses digital encoding so that all the data is encoded in strings of bits, which are zeros and ones, and that the physical entities that encode those digits have definitely two states associated with those things. So
So they're
one
like a
state,
switch, are they?
yeah, like a switch, yeah.
Yeah.
So, for example, a low voltage state for a zero and a high voltage state for a
Yeah.
one,
Okay.
something like that. Um, that digital encoding is just very useful for making things more robust against noise. Now, in a quantum computer, that's not the case. You have what are called qubits as the fundamental entity, and those are things which still have two states, zero and one. The big difference is that you can have superpositions of those.
So
So
that
you
means
can
they can be both in both states
have
at once.
Yes, sort of. I mean, when you measure the thing, it's definitely in one or the other, but you have to have this conception that before you measure it, there's this uncertainty about where they are. What that allows you to do is take hold of what that's called superposition, and you can utilize that to manipulate arrays of these systems in ways that are not available to a well, I'll call a classical computer. And by that I mean even the most advanced current HPCs. So so it's really a very, very radical reconception of the way that you encode and process information. And what it allows you to do is tackle problems which grow exponential in complexity as the size of your input grows, so as your input bit string grows, which therefore, if you're using a regular computer, if you double the size of your input, you would have to square the size of the computer. In a
Mhm.
quantum computer, you double the size of the input, you double the size of the computer.
Oh,
So it's a for certain classes of problems, it provides this ability to tackle exponentially complex sort of calculations, and that's the sort of big promise, at least in an application sense.
yeah.
But I would add that there's I think, a really important scientific reason as well, which is the following, that in building these machines, you are building a palpably macroscopic quantum system over which you have control.
Mhm.
And by
Because
definition,
so
there's
when we
no
think,
way
just
that,
for our listeners, when we think of quantum, we're thinking at the very, very tiny scale. So we're thinking electrons, we're thinking photons, that sort of thing. But when you say macro, you've now actually got a big object that's behaving like those small objects do in the fact that they're in the superposition of states. Is that right?
yes, that's exactly right, Tim. Yes. So you're right that the entry into the quantum world we tend to think of as being very tiny things, very could be very high energy scale, but still very tiny objects. And of course, the famous thought experiment is that of Schrödinger, which interestingly he came up with while he was a resident in Oxford between 1933 and 1936, which was his famous cat analog. And he said, well, this superposition we know works for these small atomic systems, but we never really see it in the everyday world. So the idea that a thing like a cat could be simultaneously dead and alive is not an intuitive concept. It's not an experience we've ever come across.
You've clearly never met my dog. I often have to go and check whether he's alive.
Yes, and then presumably your dog becomes with the cat an entangled state of dog excited, cat not, and vice versa.
Yeah.
Yeah, yeah, indeed. So yes, and he used that in discussion with Einstein about the sort of strangeness of the way the quantum world was described, because it clearly doesn't doesn't obviously fit with our everyday world, everyday experience.
But
But
this,
the
sorry, so but so these large quantum computers give us a possibly a route into that, right?
Yes, that's exactly right. And
Hmm.
so you could start to build systems whose properties you can't study any other way. And therefore, the opportunity for developing new science, new discovery, new understanding, I think is very great as well. And I think that dual aspect of opening worlds on new discovery and new important applications is a really exciting sort of thing.
So do they work yet? I mean, you've talked about the sort of theoretical background.
Yeah.
Can you obviously you can't go down to Apple and or Dell and buy one yet, but
Yeah.
they are in production, and and can you have they been demonstrated to work well for some classes of problem?
Yeah. Well, th this is a very interesting question. Now, if you told me, if you said, I would like to go and buy a quantum computer, there are companies that will sell you them,
Right.
and indeed you can access them on the cloud. Now, are there computers that will outperform any classical computer? I think that's a more subtle question. I mean, the general answer is no, not yet. So you're not going to get a general purpose quantum computer that is big enough and robust enough to outperform any any existing HPC or future HPC. That's just not yet possible. But there are certain classes of tasks where computers have shown the ability to do things beyond the capability of any HPC, high
Right.
performance computer. But those are an extremely restricted range of tasks. Nevertheless, it's an area which I think is of increasing importance, which is the role of quantum processors within a sort of quantum classical hybrid machine learning environment. So it's slightly hedged. I would not go out and listen to anyone who says they can sell you a full fault tolerant quantum computer.
But
But
Ian,
if you had a particular specialized task, you might find a machine that does something that's valuable to you.
so Ian, what's stopping them from achieving this potential that we know?
Yeah. Yeah, it's an extremely important question, Simon. So let me go back to Schrodinger's thought experiment. Why is it that we never see things like a cat in a superposition state? And the reason is that we can never isolate the cat sufficiently well from the environment and have sufficient control over every parts of the cat that it doesn't sort of just thermalize its energy and dissipate everything. So and it's extremely difficult to isolate things in that way. Now you certainly can do it, and you'll know from your own experiments and work that that's possible. If you take a helium fridge and you cool it down to millikelvin temperatures, you can certainly get superconducting states or superfluid states, things that are clearly macroscopic quantum states. But you have very, very little control over what they do. You can measure general properties of them, but you can't control individual atoms. So you have simultaneously this problem where you want to isolate things really, really well so that nothing leaks out into the environment. And you want to be able to control things at the individual level of atoms. And that's proved quite hard. And I'd say that there've been two over the past 30 years, there's been two major steps which have allowed that. One was to show that even if you haven't got things perfectly isolated, you can still control the errors without destroying the quantum properties. And that's a area called quantum error correction. And indeed, colleagues at Oxford made major contributions to that area in the 90s. So that's conceptually. That says physically, we don't know of a reason why you can't build one of these machines. But the engineering you need to actually make that work at a scale that you'd like and a scale that will be useful is extremely fierce. And that is where people have been putting a lot of effort in over the past 20 years. And, in some ways, it's just remarkable how far they have gotten. There are indeed machines at uh, Google, at Microsoft, at IQN, various other places where there's superconducting machines that have sort of more than 1,000 qubits in them.
Okay.
Again, not fully controlled, not all fully linked up, not working properly, but they've been able to show that using these error correction techniques, you can slow down the rate at which stuff dissipates into the environment and still do calculations. So
So,
this is remarkable, really.
so one thing that our listeners, are probably thinking at this point is, we've got artificial intelligence is another area in computing that's, become widely used with large language models, things like ChatGPT. Some people are nervous about, artificial intelligence, these large language models becoming sentient. Now, there's also kind of connected to that, I'm a biologist, there's some arguments out there that actually the human brain uses quantum properties, particularly of neurotransmitters and what have you, in order to come up with consciousness. So, is there a risk or a likelihood or a probability, do you think, of getting to a point where we can couple quantum computing with large language models to make artificial intelligence that takes over the world and kills us all?
Tim has a very unhealthy obsession with taking over the world.
Yes. I think, Tim, you need to explain your background too. Yeah. Let me separate that into two parts. The first part being, what does the intersection of quantum and AI or quantum and machine learning look like? And that bit, I think we can have a conversation with some grounding in it. The second is, does that make AGI more likely, and does it make consciousness more likely? I'm going to probably pass a bit on the latters
Fair
because
enough.
I don't really quite know what either of those terms really means. But I will say on that latter that one thing I think these domains do for us is they make us rethink in new ways how we think about how we look at those concepts. I think that's actually really valuable to think about. On the former, I think this conjunction is going to be valuable. And one of the ways in which it's valuable is that when when you are training your artificial intelligence, your neural networks, you often you have data sets and you have sort of random collections, and you're trying to sort of classify these things. And it turns out the sort of random bases that you can generate are different from quantum computers than you can get from classical computers. So I think there are ways in which this conjunction does help you improve machine learning systems, and therefore, in principle, can help you improve AI. I'd say that's still very early days yet, but there are some interesting examples where that will work. Whether that plays over into AGI, I really don't know. So
I would be
watch.
skeptical personally.
Yeah,
I'll just have to take over the world myself.
yeah. That's well, Tim. I'd rather you took it over than some faceless computer somewhere in a deep state.
Yeah.
I'm not so sure, Ian, to be honest.
Okay.
So, Ian, I had a question. I'm just wondering if you can explain to our listeners, so what we could expect a future quantum computer to perhaps look like. would it look like a conventional classical machine?
Hmm. Um, so so no, yes and no. So I'm hedging, right? So so the first point to note is that I talked about how you have to really isolate these things to keep them in these quantum states. There are several ways that you can do that, but almost all of them involve having some element of cryogenics, so cooling down to 4 Kelvin or below. And many of them also require a high vacuum. So those are two elements that generally regular data centers don't worry about. Of course, they also need massive control systems, so the conventional electronics and or HVAC is also something you need. So that's one element. And those I think won't go away. The other thing to say though is that they they will likely be just as the first digital computers were quite large and quite clunky. So we might imagine the current roadmaps pointing to quite big things, I don't know, warehouse style computers or at least large room style computers first. Now, having said that, I think there are some approaches for these small scale devices that can be quite compact. So that you might have a range of processors, some that are compact and fit in your regular rack mount,
Yes.
performing very, very specialized tasks, and some that are big uh, building size entities that are your fully fault tolerant ones. So that's where I would expect first generation to be.
Wow, really is a very different concept, isn't it, to the one that we're now used to?
Yeah.
So one of the things that I do in my work and my group do is we do build simulations of
Mm.
ecological systems. So one of my postdocs at the moment, has built a pretty complicated model of multiple interacting species with for Yellowstone National Park, and it takes a very long time to run, and it's because I think it's got lots of parameters. It's this exponential problem that you talk about,
Mm.
lots of things interacting. Is that, I mean, if we could sort of simplify the problem, and that would that be some at the moment we can't do it, but is that the sort of problem that it might be possible for quantum computing to be able to address at some point in the future? Or, I mean, I know I haven't given you any details of exactly how they all work or the
Yeah.
equations behind them, so it might be an impossible question to answer. But
Yeah.
I'm just wondering, in the sorts of things that I do, whether quantum computing is likely to be helped within the next sort of 10 or 20 years.
Yes. It certainly is. It certainly is a possibility, and you're right. The details are important here, but there are classes of partial differential equation solvers that work more efficiently, so are much faster and tackle different sorts of problems on quantum computers.
Okay.
There are certainly optimizers, so variational
Yeah, yeah.
sorts of algorithms that work much better on quantum computers as well. So I think this sort of opens a really interesting question, Tim, which is how many applications are there where a quantum computer will be really necessary versus one where it would be nice to have, and those where actually better classical algorithms will do just as well.
Yeah.
And I think that's still an open question, and lots of people are working on that at the moment.
And so, putting the sort of AI stuff aside, are the bits in everyday life that our listeners who have got an iPhone or got a mobile phone that's packed full of computation, they've got a laptop at home, is it going to change their lives in sort of many ways in terms of computing that they can do? Is it going to be, I don't know, easier to, I'm trying to think of tasks that might take them a long time on their existing computers at the moment
Yeah,
that might speed up significantly again in the next decade or two? Or
yeah.
is it going to mainly be in universities where people are trying to solve high dimensional problems with lots of parameters?
Yes, let's see on the latter. I think if there's not some major societally valuable problems that quantum computers to solve, they're not likely to be built for just universities alone. I
True
think they're
that.
too
That's
expensive for that. Uh, but as Simon was asking earlier, scale. I think what's clear is that at least in the next decade or 2 decades, these are going to be things that you'll have to access remotely. They're not going to be small enough to fit in your own computer. However, I think may be interesting is that other areas of technology in which quantum is making a difference are around things like timing and positioning. So ways in which you can build
mm,
GPS-free navigation, for example, to the same sort of precision. Second area is in communications, so secure communications, point to point, or even over networks. And I think those are plausibly technologies which might allow you in handheld or desktop devices to access these quantum computers in secure and remote ways that would allow new capabilities. So, are your bank transactions more secure by using this sort of quantum encrypted random numbers that you carry around on your phone? That kind of thing that you might be able to see.
Simon, we're running out of time. Do you have sort of a final question or any additional thoughts?
I'm trying to think. One area where I was wondering, and again, this will show my ignorance. Is it likely to help in things like, for example, like weather predictions? And we sort of, I know that sort of one of the biggest computers right now in the UK is owned by it's run by the Met Office. So things like, will we see changes there? Do you think?
Mm. Yeah, that's a good question. And I am intrigued by this area because, of course, what you're looking at is can you solve systems that are intrinsically chaotic? And these are generally classed as sort of uncomputable. So you can get so far, and the bigger computer you have, the bit further you get. Now, now, machine learning has certainly made a difference to weather prediction. And I think this combination of machine learning and model underpinning will will benefit from quantum computers. However, I'm not myself convinced that you will be able to fully solve a chaotic problem on a quantum computer. You might get a bit further, you might get substantially further, but I'm not sure that you'll be able to tell what the weather this time next year is going to be. And certainly you can't do climate change yet.
No, well, we're running out of time, Ian. Thank you so much for taking time to join us and to chat about this. It's been really fascinating, and I know that there's a lot of information out there about quantum computers. So thank you very much for making it accessible to our listeners.
Thank you very much for the opportunity to chat. It was great to see you.
Oh, well, that was interesting, Simon, wasn't it?
Yeah, definitely. I mean, I'm still trying to get my head around what these things, these quantum computers are going to look like. It's still a bit, we've got this idea of sort of big machines, smaller machines, but then this idea that they're still going to need, freezing, basically. There's this cryo aspect. And yeah,
And
it's
in a
kind of,
vacuum and.
yeah, I'm finding it hard to get my head around, to be honest.
But it sounds like, from what he was saying, because your work, you end up, simulating to try and understand how different molecules interact with one another. And I mean, you told me before that you sort of fudge over the quantum side a little bit in terms of the way that you do that. But from what he was saying, types of problems that they can address, it could revolutionize your field, I guess, once you start actually possibly being able to bring in some of that quantum behavior at the level of atoms.
Yeah, I think so, absolutely. So at the moment, what we struggle to do is, like you said, look at the quantum effects and new chemical bonds being made, for
Mm.
example. And if it starts enabling us to look at the effect of electrons, and that changes everything.
But it sounds like the challenge they have at the moment is getting all these qubits. Was that it? Qubits or
Qubits.
qubit, not a quidditch, a qubit. Getting all of these qubits to behave. So I guess they obviously they misbehave, which is why they've got all this error correction. So it's trying to try and it's a bit like herding academics, I suspect.
Yes, I should imagine so. But it's just conceptually for me mind-blowing. So we think of a computer I always tell my students the computer only does what you tell it to do.
Mm, mm.
Right? Don't blame the code or don't blame the computer for the simulation not working. But here, you can't actually control every aspect of these machines, and that's kind of the opposite to how we think of computers.
Yeah, no, it's true. It's like computer says maybe rather
Yeah,
than computer says no.
that's an excellent analogy.
Well, I mean, it sounds as if it's still some way off, but I mean, hopefully our listeners who've heard about quantum computers, have kind of learned a little bit more about them. And I mean, it's interesting that they could help in years to come improve machine learning and AI and what have you. I mean, it's a bit frightening, but although I'm a bit skeptical, to be honest, about AI taking over the world.
Yeah, me too. Me too. I think the idea that it opens up our eyes to this unseen quantum world for me is super exciting.
Yeah, no, I think that's right. Anyway, I'm off on a trip, so I'm going to be away for a little bit, but we'll get back recording on my return.
Cool. Stay safe, Tim, and see you when you get back.
Yeah, okay. Thanks, Simon.